Want to ace tree questions at Google, Amazon, or Apple? Binary Tree Level Order Traversal is a classic pattern mastery 100 question. And over 25% of candidates mess up the queue logic or output formatting. Nail this one, and you'll be ready for everything from graph traversals to real-world scheduling challenges. Let's level up your skills together. Let's solve binary tree level order traversal with the basic method, so you build rock-solid, interview-ready solutions every time. Let's break this down. Given the root of a binary tree, return its values level by level, that is nodes at each depth together in a list. Input, root node of a binary tree. Output, list of lists. Each inner list contains all node values at that tree level. Here is an example. Input, output, 3, 9, 20, 15, 7. Here is a real-world example. Suppose you're managing a project with tasks organized in dependency levels. You want to group tasks by which ones can be started at each phase. An interviewer might ask, how would you organize a company's org chart into management levels for communication planning? Now let's assess it. What's tricky? This is a classic breadth-first search, BFS. You need to process the tree layer by layer. You need a queue to keep track of which nodes to process next. The result must be grouped per level, not just a flat list. Think step by step. If the root is null, return an empty list. Initialize a queue with the root node. While the queue isn't empty, track the number of nodes at the current level. Queue size at start of a loop. For each node at this level, pop from the queue, add its value to a temporary list. Add its left/right children to the queue for the next level. After finishing this level, append the temporary list to the final result. Repeat until all levels are processed. Let's add more detail. Why track the queue size at each loop? It ensures that you process exactly the nodes at the current level, so your output matches the level grouping. Forgetting this step is a classic source of bugs. Some edge cases. Empty tree. Return. Single node. Return. Val. Deeply skewed or unbalanced trees should still work. Here is the structure. If root is null, return. Initialize a result list and a queue with root. While queue not empty, get current level size. For each node at this level, pop, save value, in queue children. Add this level's binary tree level order traversal. Let's try to implement it using solution 1. Line by line narration, line highlighted, class solution. We begin by defining a class called solution, just a container for our function. Pause. Line highlighted, def level order self, root. This defines our function level order, which performs a level order traversal of a binary tree, meaning we visit the tree level by level, from top to bottom. Pause. Line highlighted, if not root, we check whether the tree is empty. If there's no root, there's nothing to traverse. Pause. Line highlighted, return. If the tree is empty, we return an empty list because there are no levels to report. Time complexity note. This check is 01. Pause. Line highlighted, result equals, this initializes an empty list called result, which will eventually hold all levels of the tree as separate lists. Pause. Line highlighted, queue equals, root. We create a list called queue and start it with a root node. This queue will help us process nodes in first out order, perfect for level order traversal. Pause. Line highlighted, while queue, this loop continues as long as there are nodes in the queue. Each iteration processes one full level of the tree. Time complexity. Every node enters and leaves the queue once on. Pause. Line highlighted, level underscore size equals len queue. Here we record how many nodes are currently in the queue. These nodes represent all the nodes on the current level of the tree. Pause. Line highlighted, current underscore level equals, we create an empty list to collect the values of the nodes at the current level. Pause. Line highlighted, for underscore in range level underscore size, this loop runs exactly once for each node in the current level. We'll process them one by one. Pause. Line highlighted, node equals queue.pop 0. We pop the first node from the queue. This gives us the next node to process. Note, popping index 0 is on, but since the total work still involves processing each node once, we treat total complexity as on. Pause. Line highlighted, current underscore level dot append node dot val. We add the node's value to the current levels list. This is what we'll eventually store in the final result. Pause. Line highlighted, if node.left, we check whether the node has a left child. Pause. Line highlighted, queue.append node.left. If it does, we add that left child to the queue so it gets processed in the next level. Pause. Line highlighted, if node.right, we also check whether the node has a right child. Pause. Line highlighted, queue.append node.right, and if so, we add the right child to the queue as well. This ensures both children will be included in the next wave of nodes. Pause. Line highlighted. Result.append current underscore level. After processing all nodes in the current level, we add the entire levels list into result. Each iteration of the while loop produces one row of the tree. Pause. Line highlighted. Return result. Finally, after all levels have been processed and the queue is empty, we return the full list of lists representing the entire level order traversal. Pause. Final wrap-up. And that's how this algorithm works. It first checks for an empty tree, then uses a queue to process nodes level by level, collecting values into separate lists for each level. Efficient, simple, and elegant. Highlight input box. Root equals 3, 9, 20, null, null, 15, 7. Let's test our level order traversal function using this binary tree. 3, 9, 20, null, null, 15, 7. This level order array describes the tree as follows. 3 is the root. 9 is its left child. 20 is its right child. And under 20 we have 15, left, and 7, right. Explain the logic briefly. Our algorithm processes the tree level by level, collecting the node values at each depth into their own list. So the traversal looks like this. Level 1, 3 level 2, 9, 20 level 3, 15, 7. These groups are exactly what a correct breadth first traversal should produce. Highlight output box. Output, 3, 9, 20, 15, 7, expected, 3, 9, 20, 15, 7. And the result matches perfectly. The output aligns exactly with the expected value. The test case is accepted. So, our implementation is correct. The algorithm walks through the tree level by level and gathers nodes cleanly and accurately, efficient and spot on. Now let's try another implement approach using solution 2. Line highlighted. Class solution. We begin by defining a class named solution, which simply organizes the method we're about to write. Pause. Line highlighted. Def level order self. Root. This function, level order, performs a level order traversal of a binary tree, but instead of BFS, we'll do it using DFS with level tracking. Pause. Line highlighted. If not root, we start with a simple check. If the tree is empty, there are no levels to traverse. Pause. Line highlighted. Return. In that case, we return an empty list because the output should contain no levels. Time complexity. Base case is 01. Pause. Line highlighted. Result equals, we create an empty list called result. This will eventually store multiple lists, one list for each tree level. Pause. Inner DFS function. Line highlighted. Def DFS node, level. We define a helper function named DFS, which stands for depth first search. It takes two arguments, the current node, and the level we're currently exploring. This DFS will collect nodes by their depth level. Pause. Line highlighted. If not node, if the node is empty, we stop immediately, no work needed. Pause. Line highlighted, return. This simply exits the current DFS branch. Pause. Line highlighted, hash if this is the first node at this level, create a new list. This comment explains the next piece. If it's our first time reaching this depth, we need to set up a list to hold nodes from this level. Pause. Line highlighted, if level equals len result, this checks whether the number of levels recorded so far matches the current level. If they're equal, it means this level has not been created yet. Pause. Line highlighted, result.append, if so, we add a new empty list to represent this new level. This ensures each level has its own list. Pause. Line highlighted, hash add current nodes value to its level list a comment reminding us that now we place the nodes value into the correct level. Pause. Line highlighted, result level. Append node.val. We add the current nodes value to the list corresponding to the current level. This organizes values exactly as level order traversal expects. Pause. Line highlighted, hash recursively process children at next level. This comment explains that we now move deeper into the tree. Pause. Line highlighted, DFS node.left, level +1. We recursively call DFS on the left child, but notice we pass level +1. This means we're going one level deeper into the tree. Pause. Line highlighted, DFS node.right, level +1. We do the same with the right child. Together, these two recursive calls ensure the entire tree is explored depth first. Time complexity. DFS visits every node once on. Space complexity. OH for recursion stack, where H is tree height. Pause. Trigger DFS, line highlighted. DFS root, 0. We start the DFS from the root at level 0, the top of the tree. pause, line highlighted, return result. Finally, we return the complete result list, which now contains one list per level, filled in with node values exactly like a level order traversal. Pause. Final wrap-up. And that's how this algorithm works. It first initializes an empty result and a DFS helper, then recursively collects nodes by their depth level using a depth-first traversal. Efficient, simple, and elegant. Highlight input box. Root equals 3, 9, 20, null, null, 15, 7. Let's test our level order traversal function using this binary tree. 3, 9, 20, null, null, 15, 7. This level order array describes the tree as follows. 3 is the root. 9 is its left child. 20 is its right child. And under 20 we have 15, left, and 7, right. Explain the logic briefly. Our algorithm processes the tree level by level, collecting the node values at each depth into their own list. So the traversal looks like this. Level 1, 3 level 2, 9, 20 level 3, 15, 7. These groups are exactly what a correct breadth-first traversal should produce. Highlight output box. Output, 3, 9, 20, 15, 7, expected. 3, 9, 20, 15, 7. And the result matches perfectly. The output aligns exactly with the expected value. The test case is accepted. So, our implementation is correct. The algorithm walks through the tree level by level and gathers nodes cleanly and accurately, efficient and spot on. Let's quickly recap binary tree level order traversal, a must-know interview question that tests your understanding of queues and BFS traversal. The goal was simple: traverse a binary tree level by level, grouping nodes at the same depth together into lists. Essentially, we built a layer-by-layer view of the tree. We recognize that breadth-first search is the perfect fit, using a queue to process nodes in order, one level at a time. The key challenge was keeping track of the queue size each round, so we only process nodes from the current level. Our plan: check for an empty tree, initialize a queue with the root loop until it's empty, collect values for each level, and in-queue child nodes for the next round. We wrote this logic step by step, using a clean BFS loop and a result list, and it ran smoothly on LeetCode without any errors. We verified the output, each level printed correctly, from top to bottom. 3, 9, 20, 15, 7. Edge cases like empty or single node trees worked perfectly. The big takeaway? Queue-based BFS isn't just for trees, it's the backbone of level order logic in graphs, scheduling systems, and even social network distance calculations.